we would like to prove linear independence of the solution set in this case, right? Which is, so we've got what, like e to the alpha 1 zeta, zeta e to the alpha 1 zeta, zeta to the what? M1 minus 1 e to the alpha 1 zeta, and so forth, right? E to the alpha 2 zeta, and continuing on down the story, right? You get all these, why is that linearly independent of the algebra? So, I mean, you could just try to calculate the Wronskian like directly, that sounds horrible. What I chose to do instead was to actually look, I set eta equal to 0, the box equation equal to 0, and then I gave explicit arguments to prove that that implies that Cij is equal to 0 for all ij. So I proved that the trivial linear combination of the functions must have trivial coefficients. Mm-hmm. And the way I did that, if you look at the argument, is to take this equation and pick on it by operating on. So like I said, T1, for example, is L over D minus alpha 1. I should put some quotes around that. That's just like a notation for saying that T1 is D minus alpha 1 to the what? M1 minus 1. And then everything else is the same. So what happens when you take that operator and you operate on eta? Well, see, that will kill everything. Mm-hmm. Except
the product term.
Yeah, except for like the top solution in the alpha 1 case. So like T1 acting on eta, it just ends up giving you like the C1 J equal to M1. C1 M1 golly. I guess I should. Oh, look, there it is. Equation. It's kind of a bit. It's actually kind of a lot. There it is, right there. See.
63.
63. So it gives you C1M1, and then now you see why I'm having trouble thinking through it. You get alpha 2 minus alpha 1 to the M2, alpha 3 minus alpha 1 to the M3, and so forth and so on. So like. The top term. So we're tracking what happens to the C1, M1, and that has the function tied to that is z to the M1 minus 1 e to the alpha 1 zeta, right? So basically, this is the sole survivor of T1 acting on eta.
Okay.
So this is T1 of C1 M1 zeta to the M1 minus 1 e to the alpha 1 zeta. Like that is the only term that doesn't just get killed by T1. And when you let this function get hit upside the head by these guys, what happens is you get C1M1 alpha 2 minus alpha 1 to the M2, alpha 3 minus alpha 1 to the M3, and so forth, alpha k minus alpha 1 to the mk. And then, of course, from alpha 1 itself, you get m1 minus 1 factorial. Now, and all of that gets, you still have your residual e to the alpha 1z. Now that's all equal to 0 too, because you're assuming that, you know, you're assuming that this is equal to 0. You're trying to prove that implies the coefficients must all be 0. So you take that, you operate on that by T1. T1 kills everything except for this leading term. And then when you actually feed that into the T1, you get this. And so in ordinary differential equations, these are just distinct, the product of distinct roots. So like this is a non-zero number, bam, you got C1M1 is non-zero. And then you can just descend down. You can, instead of dividing by d minus alpha 1, you can divide by d minus alpha 1 squared, and that will get you the next term in the alpha 1 series. And you can just kind of down like that. But the trouble is here in the algebra, these are the difference of algebra numbers, right? And this
you could do 0 dividing.
exactly. If these were 0 divisors, I don't have to have, if this is 0 divisors, then this can be a 0 divisor. The product of them being 0, it's not being non-zero. So that's, but if I have the difference of all the successive roots are units, then I can cancel these, and it forces that to be 0. And if you can do it for the top term, you can descend down, essentially descend. The argument, but you know, it's
Good.
it's not trivial to really do all the details. It'll take you a little while, but all right. So in summary, if the polynomial is the product of linear factors whose corresponding zeros are corresponding zeros differences are units, then we have a clear path to construct a solution. But even in the case that A is equal to, well, let's see. Oh, okay, in the case A is equal to the reals or the complexes, we're done because, you know, we just need distinct. Distinct is non-zero. I mean, this condition that alpha I minus alpha j, this condition reduces to distinctness over a field. Because the only way you can have things not, everything that's non-zero is a unit, right? So this just becomes not equal to 0 in a field. This not equal to 0 is the same as alpha I not equal to alpha j, just to say they're distinct. So over a field, this just reduces to distinctness. But now example 5.6 is the, you know, this is where we get into trouble.
Not I'll follow.
You're too gullible. So example 5.6, we have d squared minus 1. So you could either factor that as, you could factor that as d minus j times d plus j. So here, j squared equals 1. So we're in the hyperbolic numbers here. So that's one way we can factor it.
Yeah, that's 0. No, it's not. Correct. Almost 0.
All right, so actually this may not be. Of course, we can also get d plus 1 and d minus 1, right? So let's see here. Actually, I think this may actually not be a productive counterexample. So this would suggest, I mean, maybe this is an example of the theorem going okay. I mean, what I'm trying to say is that these factorizations may not run into the issue. So this would be something like alpha 1 equal to j, alpha 2 equal to minus j, right? So alpha 1 minus alpha 2 is what? It's j minus a minus j, 2j, which is, you know, this is a unit, right? It's not, no problem there. The multiplicative inverse of 2j is just 1/2 j. So, so 1/2 j is 2j inverse, not a problem. You know. These are units, and of course, this one, alpha 1 minus 1, alpha 2 is 1. And again, the difference there is minus 2, again, a unit. So, but all of this, I think this example does illustrate something that's a little bit disconcerting, which is you have solution sets. Well, we could write e to the jz, e to the minus jz, right? Or e to the minus z, e to the z. These are both legit solution sets, fundamental solution sets for the problem. Because we have distinct roots. Excuse me, I can't say that. We have roots whose difference are non-zero. All right. Now, on the flip side of things, these, if you take a set that contains all of this, there has to be linear dependence, right? Like,
Yeah.
or just take either one of these and plug it in, put it in here and make 3 things, it's a linearly dependent set, right? But how would you write these as a linear combination of those?
That's
What's that?
no. No. Oh, e to the z, and
Right.
e to the j.
Yeah, how can I write e to the jz as a linear combination of e to the z and I mean, this is supposedly equal to C1 e to the minus z plus C2 e to the z first, like specific choices of Z1 and Z2. How would you find Z1 and Z2?
Do you draw your
So
ear?
for that, I mean, I would just say C1 is e to the j, and C2 is e to the minus j.
Use a kill to draw your ear.
What?
You were
Ear to
just
the
kidding.
j?
Oh, it's plus, right? No.
You didn't have much anything.
Right? No.
That's one stack.
No, that's plus and minus. No, you can't do that. Because they're multiplied.
Oh. Well, I mean,
It would plus, it wouldn't multiply.
you know, you just guessed.
Yeah.
You're just guessing though, right?
Yeah.
How about this? We could plug in z equal to 0.
Oh, then you get 0.
1 is C1 plus C2.
Cupid. Cupid will do.
We could differentiate this.
I'll just wait.
And then we could plug 0 into that. Then we've got 2 equations.
Yeah, C1 equal to J, or it's J plus minus C,
Yeah, so if we add
C2 equal to J plus C1, and then, so 2 C2 J.
2 C2 is 1 plus j, right?
Yeah.
C2 is 1/2 1 plus j. And so to subtract them, right?
Hmm.
We get 2C1 is 1 minus j, right?
Mm-hmm.
C1 is 1/2.
1 minus 2.
So apparently this is equal to 1/2 1 minus j e to the minus z plus 1/2 1 plus j. So this is the kind of calculation I haven't shown that. I say a short calculation will reveal that's the kind of short calculation you could do to to find those things. I would not be able to guess that, personally. I mean, there's an intuition that says that since this is the novel thing, we're writing distinct exponentials as linear combinations of the other. So that must somehow tie into the zero divisor story because this is not possible over a field. So whatever's driving this novel situation, it must be somehow linked to zero divisors. It's totally unsurprising to find zero divisors appearing in this calculation,
You can get yourself.
but
Two.
so you almost guessed this, right? You're close, like the 1 plus j, like you said.
No, I was thinking, yeah, but my thinking got me to would have got me like j minus c, j plus c, even though that wasn't gonna work. Yeah, so it was tinkling, I guess, in the right direction, but it wasn't the right way to go about it.
Yeah, and so the other thing game you could play here would be like, it's the caution cinch, and then you could simplify like
Oh.
caution cinch using the fact how j like simplifies whether it's odd or even. And you could play those games as well. But anyway, that's just an example. This is not yet illustrated. We're still in the province of theorem 5.5 though.
Yeah.
Actually, theorem. Theorem 5.7 is interesting in that this one is a place where we couldn't just use
Theorem 5.7?
example 5.7. I'll write it out. Let's look at this one. I'll leave that out.
I'm just ready to find
Find this, okay. Example 5.7. I have d minus 1, d plus j, d minus j. Alright, so, and here we're still in hyperbolic numbers. So here alpha 1 equal to 1, alpha 2 equal to minus j, alpha 3 equal to j. And of course, alpha 1 minus alpha 2
Hello, Mom.
is 1 plus j.
the?
Alpha 1 minus alpha
That's
3
never mind.
minus j, right?
Yeah.
So these are-
zero divisors.
Exactly, these are troublesome.
Two. Okay.
So it turns out we can actually not use e to the z, e to the minus jz, and e to the jz, e to the minus jz, the solution set. So like e to the z, e to the minus j, or e to the jz there, or minus jz, e to the jz will not do. Now that theorem 5.5 doesn't actually say that, but it turns out that when the condition is not met,
So this.
it's usually the case that it doesn't work.
This is a different flavor.
Now, the funny thing here
Sure.
is you can trade this one.
Yeah,
You just do, okay, well, that's really d minus 1 times, this times that is d squared minus 1.
Oh.
So, like, yeah, you can just kind of circumvent the difficulty and go, oh, well, that's d minus 1
I
squared.
found an example where you can't circumvent it.
Yes, that's the next one.
Oh.
So this is, you have fundamental solutions at e to the z, z to the z, e to the minus z, that'll do, that's a fundamental solution set because the difference of the roots here is plus or minus 2, and hooray. But yeah, I think example 5.8 is where we finally get put in our place.
Yeah.
So we'll come back to that right after lunch.
I was just